Okay, good afternoon, everybody. Thank you very much, really, for the invitation and for being here. My talk is going to be about image processing method, making a stress in quality check, and certainly also considering that we are in the inaugural workshop of a facility, I'm going to make a point about how the new approaches to image processing in microscopy have a huge impact in facilities, and really also how we are entering perhaps a new time in the sense of EM software resources on the web. Just talking about facilities, I am coming from the National Center for Biotechnology, which is part of Instruct, and the very good news to share today is that this week Instruct, the Distributed Research Infrastructure for Structural Biology, has become a European Research Infrastructure Consortium. Is news from about 2 or 3 days ago. So that's very good thing, and probably it will mean more support from infrastructure at the European level. Let me make a point about EM that certainly you all know, but let me phrase it in a way that I will use later. This is actually sort of the pledge, as we say, of cryo-EM. We have our macromolecules in a amorphous size. They are trapped there. You see that each of them is in a totally different orientation. Of course, they were in the sample. They have been frozen. They don't have any reason to be in the same orientation. So they are, in principle, in unknown relative orientation one to the other. And of course, since we are imaging each one of them, and EM is a technique in which we can really see each of the individual molecules, we can follow eventually motion. We can follow flexibility, and with other ways, we could start linking that with biological function. My point here that I will be using during the talk is that you see how the different macromolecules are in different orientations, and to come to any 3D reconstruction, to any estimation of the 3D structure, we have to be able to sort them and relate them together, relate the different orientations. A few numbers that you certainly know already, but I am introducing also here the EMDB, the electron microscopy database. That is our section of PDB, and these graphs are directly taken from EMDB. You see here the number of structures, how they have gone over the years, and how something happened really around 2012 that made the number of structures larger, and also the resolution. At this moment, almost 20% of the structures are below 5 angstrom resolution. So this is a fact. And what has happened? Well, many things has happened, and Siran was talking about evolution, and certainly everything has a history behind, coming from the 80s. The cryogenic techniques for specimen preparation, microscopes that were every time better and better. Certainly the huge revolution in EM and also in X-ray of the new detectors, and this has been addressed by Shores, and this has been probably the change in the game that has happened. However, I should also point that we have developed, as a field, a number of new image processing approaches that have enabled us to sort conformational sorting. I mean, the flexibility to follow flexibility from the images, and to be able to fully relate three-dimensional orientation in the different specimens. From the facility point of view, let me make a particular stress on 3 issues. Data management. Data management is something that in a place like this one, like the SRF, the place of a large infrastructure, is very well known. You can say now electron microscopy is delivering terabytes per day. Yes, but the introductory talk of this workshop was telling you that this synchrotron has 40-something beam lines, and each of them was delivering also a lot of data. Terabytes or not, but a lot of data. So really, for an organization, it's very important how you manage that data. And certainly, the cryo-EM come here and is going to deliver data, but there are going to be many MX beamline, there are many other structural biologies, and the data that are going to be provided have many points in common and a number of points that have to be made differently. So they need to be related, the cryo-EM data, with other data sources like MX, like SACS. Then data throughput. From a facility point of view, and this is not working, basically the pointer, from a facility point of view, data throughput is important. I mean, we need to maximize the number of images, if you want, per shift. Defining shift per day or whatever is the standard way to measure time. But we need to increase the number of images because there is a large international community there. And of course, we have to work with a high quality standard unless we clearly work along the ways to have automatic means to widely accepted means to check for quality. It's difficult to imagine a facility to be really productive and to be having an impact on users. So, thank you, Sharon. Okay, we have worked for many years in software development, method development. Traditionally, we have made them part of a software system called XMIP, and now we have made something else, that is, how can we relate different software packages in something that now we are, within quotation, marketing with the name of Scipion in Spanish. That is actually a very famous Roman general that made very important things. We thought we could do similar things with that software. So we have different flavors of Scipion running there. That is important because I will be referring to it later. Data management. What do I mean by data management, and what have we done for data management? When we talk about data management, the notion of laboratory information management systems comes into play. How do you care for tens of hundreds, thousands of terabytes, and really you are able to follow what has been done with them, what has been done with them, the preprocessing, things like that. We have addressed that issue by interfacing our software with one of the laboratory information management system, iSpy-B. What you see here is how it's being used in Diamond. And iSpy-B is very nice to talk in this context because it was actually a collaboration between the SRF and Diamond. So what we do is all the pre-processing steps, the ones that are done at the facility, are actually dumped into iSpy-B, and then iSpy-B normal web interfaces are used to present the data to the user. Data throughput. What do we do in data throughput? What we do is the definition and construction of a number of pre-processing workflows. The idea is that while you are acquiring the data, we are making a number of computations that make things fast for you later on to get structure, but also are making continuously quality checks, as you are going to see later. And in this way, what we want to maximize is the throughput, is the capability of a facility to produce data and to know the quality of the data that are being delivered to you. Another view of data throughput. Well, you've seen that we have a number of software suite, that the electron microscopy software may be different from the EM software that, to the X-ray software you are used. What about if you could forget about installing any software? Well, that's what you can do now with the cloud virtualization. No? And this is what we do now with the Amazon cloud and with the European academic cloud, with the EGI. At this moment, it's perfectly feasible to have the data, to have, with no installation over the web, access to a very large set of programs, and to have a complete pipeline of working totally in the cloud without any complicated or potentially complicated installation. Let me go back to quality. Quality. The notion of quality and why in 3D electron microscopy. As in most of the fields, if you want to have a result, you are going to have that result. The problem is which is the quality and the reliability of that result. And there we have started from the very beginning, from the notion of getting your image to actually getting the final model and even getting the map. Let me present you the last work, perhaps, that is still not published, on a very simple thing about attaching a quality string to the data you are collecting. Well, in an extremely simplified, that is actually the way we treat the images, in a very simple linear approximation of understanding the image or the video that you are recording at the microscope. Your recorded video is going to be related to your ideal video in the most simple of the models by a gain image. Okay, how precise and is that calculation of the gain image that you have done? Has it changed in any way during data collection? Well, we have approached that, and we have been able to develop something that is able to provide us an estimation of the gain image without measuring the gain image. And really, we have checked that this works very well. These are deposited gain images, and these are computed or estimated gain images. They work very well. They are able to provide good estimation of what are your gain images, and we have used them not to so much estimate your gain image, but as put it in the normal procedure in the lab in which you have already estimated your gain. You have corrected your gain. So if you have done everything correct, if now I re-estimate the residual gain, I should have something flat. Okay, in many cases I have. In something like 20% of the cases in the EMDB or the Empire database, I get things like that should be flat and are not flat, meaning that really gain correction in no way was properly considered. If we would have been at that moment in the position to incorporate this into quality controls, the facilities would have been in the position to say, well, something is going on not correctly at the data collection level. How do we handle that in our software? Well, we just put it here in the pre-processing workflows, and movie gain as one of the objects that you are, one of the steps of your workflow. This is a very simple dialogue, and then we are putting out some statistics that help you understand how everything is going on at the level of data collection. But coming back again to quality. Quality, and I have already shown you this image, is actually the eyes and the macromolecules at the different orientation. A key step, and is the one I'm going to address now, is your capability to find correctly the relative orientation between these macromolecules. And you are going to do it through some optimization process, in which you are going to define some cost function, something that you want to maximize. And well, normally your space of solution is something like that. So it has a number of local minima. How can you try to avoid some of these local minima? Well, through some exhaustive procedure, perhaps. Also, maybe by trying to approximate your landscape of solution, but something smoother, that, however, still the global minimum, the estimation of the global minimum would be the same or very similar. And this is what we did with shores at the very beginning. It was the first time that we used a statistical method in image processing for the alignment and also for the sorting. And this later on in Shore's lab resulted in Reliant, which is really a standard at this moment. But the whole idea was, how do we escape these local minima? How we make another landscape of solutions? A few years later, now, we wanted to ask another question. How accurate is really our accuracy and precision? How good, in a general sense, are we estimating these 3D orientations? And actually, we started from simple first principle, and we addressed the notion of precision. That is really how spread are your estimation of something. Well, recall this thing about the statistical method. What we were saying is, I don't want that you give me as answer that the way to relate this orientation to this one is this. I don't want one single answer because there is a lot of noise and this is not going to be stable. Give me several answers, perhaps with proper weight, things like that. That's perfect. At the beginning, you don't know. At the end of the process, reaching convergency or something that you define as convergency, you should be more or less sure of what things are. And you would like to have a solution, I mean, that most of your estimations are very close, very clustered, very similar. You do not want at the end of a statistical approach to find your orientation. You don't want to have a situation in which you don't know really where are you and you don't know really which is your orientation. Well, this was a very simple idea. It was quite difficult to implement. Why? Because each of these views, which are the projections, the electron microscopy projections, have an intrinsic level of information in terms of telling you the 3D orientation. So this simple idea that at the end of the process we wanted that most of your solution about different orientation were to be very similar. This had a problem of normalization. Intrinsically, each orientation had a different level of information. And well, we went into that problem. We eventually solved that problem, and we were able to now present a situation in which we were able to say, listen, this is your ideal situation in which we have properly taken into account the information capacity of each image. Now, and this we assign the number 1. This is actually the situation of pure noise. I mean, I have predicted your orientation, and instead of giving any good prediction, I have just put together a set of noise. Okay, this is 0, and this is actually where you are. This is actually if I try to do this same analysis, but with the experimental data. You are going to see the impact of having a number that defines precision at the alignment level that runs from 0 to 1. You are going to see that because we are going to apply that number to each of the images. And we are going to try to see what happened. I mean, really, have we been successful aligning the images? We also wanted to check for accuracy, especially considering that what I try to show here is the alignment space and the situation that perfectly can happen of having different local minima. That you are, at certain moment of the process, you may have chosen, because of your sampling and things like that, you may have chosen one of the areas around one of the local minima, while the right one would be that other one. So you have been trapped in a local minima. We tried to also work on accuracy, providing a number between 0 and 1. And now we said, fantastic, if we have a quality measure that define or measure how good are you at telling me the orientation, what about if we start applying that to a number of data sets? The first one was something perhaps from history. For electron microscopy, 2013 is history because this is before the direct detectors and all that. And Siran is laughing. This is a very important controversial issue at that time, in which GP120, the trimer that Siran was telling you about, and these are one structure from his group, another structure from another group. They are very different. So at the time, it was a controversy, which one is correct and why, things like that. Well, with our quality figures, there wouldn't have been any controversy. This is Siran thing, Siran reconstruction between 0 and 1, 0 and 1. This is the magic corner. This is the corner in which most images should be, and they are not. Very clear, black and white. So no need to argue anything. 2017, working with 2013. Can we do more? Yes, we can do more, certainly. This is something, I mean, as a field, we are, as I'm pretty sure all fields, we are very much aware of the need to go further in quality, to have internal challenges, things like that. What I'm presenting you is a challenge that is not yet finished on map quality that we started 2 years ago and it's not yet finished. And, well, OK, we have made available a number of maps, and we are now trying to get how good we can do. Can we use, perhaps, our quality measure to select those best images from the point of view of our capacity to assign orientation? Yes, this is something that we call pruning, that is selecting images. Normally, when you do pruning in EM, you don't get any results. However, maybe this is going to be better because we have something very basic informationally behind. Yes, certainly, we do better by doing this pruning, and especially we have been very successful in medium resolution data, and there the result of the pruning, I'm not getting into very many details about this. This is a working project in progress, but the results are being very good for pruning. Let me keep going with the subject of quality. Many of you could be thinking, why all this discussion about quality? Just tell me about resolution, and this would be enough. OK, if you want to not sleep during the night, read this paper. Last year is from our point of view, a very in-depth review of what we do about resolution from the mathematical point of view, the numbers we attach, the meaning of the numbers, and things like that. And you will see that we are using several measures, and we have been using several measures that, fortunately, we can put together into a context and say, OK, we are measuring things that sometimes are not common, but we know what we are measuring. A totally different thing is we start using quasi-atomic resolution or atomic resolution, and this is some faculty of 1,000 comments 3 years ago that I did on a couple of papers on that thing. So resolution, fantastic. The notion of quality and resolution, very good. The devil is in the details, and if you go into resolution, you have to be extremely careful, and at the very least, measure the same thing always. Let me introduce one thing more that is very obvious when you are working with flexible structure, is the notion that not all the amount of detailed resolution is going to be local resolution. Really, different parts of the maps are going to be different resolution, different qualities, and perhaps part of the differences in quality are methodological because something is working worse in certain part of the map. But many times they are going to have a very deep biological meaning because that area or that region of the map is simply more fluffy, more flexible. ResMap was the first approach really to get that, and it's a very successful approach. Our contribution at this first stage of making things accessible and working with a resource point of view, infrastructure point of view, and all that. Well, now, if you go to the EMDB, to our PDB part, electron microscopy part, if you go through the validation resources, you get ResMap server that points to our to Madrid, and it gives you a very simple workflow where you can upload your map and you get immediately your local resolution measure. Can we do better? Yes, of course. Because, I mean, a few years later of ResMap, we can do better. And we can ask, we want something totally automatic, OK? We want something that is able to provide filter workflows, and eventually that could be put in the middle of for instance, a fitting or modeling workflow. And this is what we did. It's called MonoRes. Hopefully soon will be out. We are using principle of monogenic signal, analytic signal, Hilbert transform, and the approach is extremely simple, extremely fast, and really provide 3D local maps as other methods do. And here we are comparing with ResMap. We are comparing the histograms of the that we obtain with respect to other maps, and with the spirit to have everything very accessible to users and very open. Very soon, when you go to the EMDB and invalidation resources, you go to local resolution, this is what you are going to get, where you will be able to simultaneously compute ResMap, monoRes, and another thing that the group of Alistair Steven and Bernard Heyman developed a number of years ago, named BlockRes. You will have the tree estimation because nothing is exactly measuring the same thing, and really, perhaps it is very good if you have different things and focusing in different aspects of the problem. And at this moment, with all these methods, probably we are doing almost our best, and maybe difficult to get much better, in the definition of quality resolution in models, which are actually the volumes. There is a whole thing that is from the models, you have to go to the atomic resolution structure through the modeling. And there was some question there, and there are people in the audience that know a lot about this, going from the maps to the modeling. And it's just to say we haven't worked there, but it's obviously a frontier that has to be very much explored. How good is a map in terms of the model it is able to sustain? I see that I don't have much result. Is something that we have done recently also with the EMDB. When you go to the EMDB and the different entries, in 3 months, that is when we went together and did that. I mean, what we did is now when you go to any entry in EMDB, you will have something that is 3D bionode available, and this will be a combination of many sources of information in a structural setting. You will have the map, the 3D volume, the atomic information, many other things, and we are very happy because in 3 months we are getting many people interested, and each people is spending almost 10 minutes looking at that. What are they looking? Well, they are looking at the structure. They are the annotation are interactively mapped into the structure, so you can really check if when you say this is my model, and there is a lot of a priori no, but from the signal processing point of view, a priori. You have a lot of data from other sources. How do they map into your model? So I go very quickly. I was supposed to do some demonstration. The people behind, Carlos, Javi has been incredibly important in everything I have shown here. He's moving to Montreal. He has just moved to Montreal. José Luis and Rubén and Pablo for all the team. Certainly always looking for people, as I suppose many people in this audience as well. And perhaps the last announcement for the first meeting on CPM4 facilities that we are having at the end of the month in Madrid, and really we hope to have a number of facilities and to study with them which are the issues that pre-processing workflows, reporting, all that have to be developed. And with that, I'm done. Thank you very much, really.
Thank you very much for a really, really nice talk. Any questions? On?
Konsu, hello.
Question about the very interesting comparison of the HIV envelope protein structure. So try to understand what you did. So you show a plot of the Sojovsky structure and also Sheeran supervenance structure.
Yes.
So those are your results, right? These are your orientation. Is that right?
Yes.
So
absolutely.
if you use this orientation, your orientation, and their data and your structure, did you get that?
If I get their data, that was quite difficult to get, their map, and with their data and their map, I calculate the orientations, and I do this sorting of orientation according to these principles, this is what we get.
So you could get this structure?
In principle, yes. I mean, this map, yes.
So it looks pretty good to me.
Yes, it looks very good to you. Fantastic.
But it's from your data. It's from the image,
but
right?
Let's see. The beautiful thing about local minima is that they are very beautiful. This is a very nice local minima, but it's totally wrong in terms of going to the global minima. So this structure is a typical example of a local minima. So it's fantastic. from the point of view of being whatever. However, from the functional point of view, it was not fantastic in many ways. But however, what I'm saying is now that we can analyze this structure considering a number of basic principles that were not put into the estimation of the structure itself, this structure does not conform with these principles.
Well, I just don't quite understand it because the structure arose from the data, from the image. I mean, they look pretty good.
Yes, of course.
It means something.
We can talk later. It's very clear.
Okay, question there?
Elena.
I think I will express nearly the same question, which will be by Sriram and yours.
Yes.
The general problem with this given molecule was that it was not the right data. And if, in general, if you have a local minima, from my point of view, the local minima possibly can reflect some kind of conformational form of the same complex. But in this case, it's a bit tricky and, from my point of view, a wrong example, because it has been shown that the molecule, the images, they didn't contain the protein.
Look at that from the facility or the database point of view. Should I have had these tools, this structure would have had a validity report, and in the validity report, for whatever reason they are, and I agree with you that the picking was probably incorrect in this case, but from whatever point of view, the validity report would be already telling you something is wrong.
But it's definitely wrong, because not just because a local minimum, which is quite close to the major.
Okay. What this structure are violating is actually exactly what I have said, that they should converge a certain functional.
I have a fundamental question about that method.
Yes.
How can you measure accuracy if you do not know the true orientation?
Oh, okay. I didn't get into the accuracy, sure. I get into the precision. The accuracy part is a much more tricky thing that we have to be. But basically what we were doing here is checking the consistency of your map that was one of the solutions with a coarse screening, a full screening at reduced resolution of the whole search space.
So precision, I can understand.
Exactly.
But
And this is
accuracy, you never know, because every particle has
that's
unknown orientation.
exactly what I'm saying. What I did explain was the part of precision because it was much easier. I didn't get into the accuracy part. The accuracy part, we can go into that. But anyway, I answer is you take your structure, and now with the structure you take that is one of the possible structure, one of the minima. We do now a exhaustive search, so we get rid of local minimization by doing an exhaustive search at a certain resolution. Sure.
Yeah, what if we did the converse of Hong's experiment? You take all these orientations and you take an initial model of the influenza spike.
Yes.
Will you get the influenza spike back?
Yes, you take.
I bet you will.
Yes.
I'm saying
yes.
that if you did so if you go back to those two plots, because we did this experiment, right? So if you take, say if you took our orientations and
Yes.
you put if you put an influenza spike back, you won't get it back. But
Yes.
in the other case, because they almost look random, the correct control experiment to Hong is that you use a model of something that's say similar kind, has threefold symmetry, but say influenza or Ebola. And then maybe you'll get that back. And that's maybe a more definitive thing than saying that you can take the next slide and get back that model, because that model had other problems with it, as we know.
Yeah, perfect. That model has many problems, but I am measuring only one. And that one is actually the consistency with a certain functional. And a priori that is saying, I like the work of that functional when it produces situation like that. I do not like the way that functional works in that data if produce result with that. So from that very well posed point of view and very well posed question, I answer that with it. And I'm saying this data set is in agreement with that hypothesis, and this data set is not in agreement with that hypothesis. And the hypothesis seems to be relatively simple and logical. Is at the end of a statistical analysis, if you are in a situation in which your statistical method is telling you very different answer, does not seem to be a data set from which you can conclude anything.
Okay, I think, unless there's any one last question, we've just about at coffee time. So, sorry, I've chosen between two people. Go for it.
About resolution. In crystallography, the concept of resolution is defined in a very univocally way. Okay, yes. So it means that if I have a structure at 2.5 angstrom resolution, it means that I have measured the amplitudes at 2.5 angstrom. Okay, yes. That's it. Maybe that the model is wrong or is, but anyhow, that's the resolution. Do you think that in cryo-EM the concept of resolution is the same quantitatively?
Well, our traditional way to measure resolution has been to measure reproducibility. So you have different data sets. You have your complete data set split into two sets, for instance, and now you measure the reproducibility. And this you go through different frequencies and all that. But we don't have a measure in Fourier space of this is our last reflection. We have measure in real space, and we try to see when, at which frequency, at which resolution, we are not able to get any more the same answer in real space.
But at the end, do you think that you end up with the same, with a number which is comparable?
Yes, yes. I mean, we are, of course, and we use it in the same manner, although the way to, the meaning is really different. But at the end of the day, of course, we are saying, listen, we are able to reproduce, we have to put a threshold here, I'm not getting into that, but we are able to reproduce up to certain frequency the structural information. So you give me different data set, I produce the same map up to that resolution. So this is what we mean mostly in the case, in the field, when we talk to resolution.
Okay, I think we're 2 minutes late for coffee.
Oh,
so I think we should probably break now. But thank you very much for a really nice talk.
Thank you.
And before you go, can all of the speakers who are giving talks in the rest of the afternoon go and see Marco and make sure that their talks are installed on the computers so we don't have any delays during the program. So anyway.